All right, so today what we're going to do is we're going to look at free body diagrams. Now, a free body diagram is basically representing an object and putting arrows on the object to show where other forces are being applied to it. All right, let's look at an example here. So, first we want to look at what a force is. Now, to represent a force, we're just going to use an arrow. Now, you see here that some people say, hey, the longer the arrow, the more force it is. But a lot of times for what we're going to be doing, we don't actually know how much force is there yet. It's one of the values we have to solve for. So we're going to kind of just draw all of our arrows the same. What is important, though, is that we put the direction of the arrow the right way. All right. So if the force is pushing an object up and to the right, like this one here, make sure that your arrow is pointing up and to the right. If we know the angle, we'll also put the angle in here. If it's straight up or straight to left or right, we don't need to put an angle, we'll just draw the arrow. And if it looks like it's pointing straight up and it doesn't have an angle, we just assume that it is up. We've already talked about moments, counterclockwise is positive, all that stuff. And we had just spent a lot of time in the last couple lessons looking at this and how to calculate moments, forces, and distances. Big thing, and I want to emphasize it again, make sure that when you're measuring the distance, that it is perpendicular right here to the force. Okay, so a free body diagram. What we're going to do is we're going to draw the object that we're making the free body diagram of, and then we're going to draw arrows on it showing how different objects are applying forces to it. Now, one of the big things to remember is an object can't apply a force on another object unless they're actually in contact. So, for example, you see the red book on top. Its forces can come from its own weight. It is in contact with itself. And the black book under it is touching the red book, so it can apply a force on it too. The blue book and the red book do not apply forces on each other because they aren't in contact. So, first step to making a free body diagram, we sketch the object. There's our quick sketch of our book. We'll just make a rectangle. And then we're going to apply arrows to show us the forces. So, we're going to say that the weight of the book itself is pulling down, and the book underneath of it, the black book there, is pushing back up. Now, we call these an applied force. An applied force is the force that's actually pushing on something, whether it's its own weight or something else pushing on it. And a normal force is basically a counteraction to that. For example, if I push down on the table pushes back on my hand, but the less I push on the table, the less the table pushes back. That's how you can tell that it's a normal force. So once we've drawn the object, the arrows, we're going to go ahead and label them. If we know the amount of the force, we'll go ahead and put that on there now. If we have something that's a little bit more detailed, a little bit more complex, we also want to put dimensions in. And you see that here, this is a truss, some triangles, and we've put dimensions on both the angles and the measurements here. All right, so we've got a sled. Some kids are sitting on it. It's being pulled by somebody, and we're going to have a few forces. So first, our representation of the sled. In this case, we're just going to make a gray rectangle. The sled itself has weight, all right? And as we're pulling the sled forward, friction is pulling the sled back. Friction wants to slow down the sled, so it's pulling backwards. The ground is holding the sled up. If there wasn't a normal force there, the sled would just fall to the center of the earth. So we do have a normal force. The snow underneath the sled is pushing it back up. And whoever's on the other end of that string is pulling the sled forward. And we'll call that our applied force. All right, so the children and their sled, we've got these basic 4 forces here on them. It's not always going to be 4 forces. It depends on the situation. And since the one is at an angle, we do want to put what the angle is. Here's a person pushing a refrigerator up an inclined plane. We want to do a free body diagram for the refrigerator. So we represent the object. Notice it doesn't have to be a detailed representation. A lot of times we even just draw a point. The refrigerator has weight. Weight is always pulling down towards the center of the earth. Since it's on an inclined plane, the surface of the plane is at an angle, so that normal force is also pushing up at an angle. Notice it doesn't matter. Over here, the normal force is on the bottom of the fridge pushing up and left. Here, they drew the force on the top pushing up and left. It doesn't matter where we draw it as long as the direction of the arrow is correct. So whether you drew it up here pointing up and left or down here pointing up and left, both are okay. And this is the person applying a force to push it up the inclined plane. Again, the arrow could go on the left side or the right side as long as the arrow is pointing right. And as we're going up the inclined plane, we of course have some friction pushing back. All right. Many of these are at angles. We would want to have the angles. So let's go ahead and look at this pulley system. We have a couple of weights hanging. We have mass 1 and mass 2. Mass 1 is hanging from a simple string, so its own weight is pulling down, and the tension in the string is pulling it back up. That one's pretty straightforward. Now, let's look at the movable pulley that holds mass 2. So here's our pulley. It has weight pulling down. Now we could have drawn this as one arrow or two. Notice they have the weight of the pulley and the weight of mass 2. They've combined them here. But you could have one going down that says weight of the pulley, and then you could have one going down that says mass 2's weight. Personally, I kind of prefer it with the 2 arrows. Like, why make it more complex and try to combine things? Then we have 2 strings pulling up, one on each side, and we draw these separate because they are 2 forces. There's the string here and the string here, and they both pull up with a certain amount of tension. All right. As we remember from before, when we talked about pulleys, when you have something like this, the tension is the same throughout the entire system. Now, we've talked about how to draw a free body diagram, and you're going to draw a couple for your homework today. But we also want to look at how things are held down to the ground, down to other objects, supported, like what holds them. And we have some basic types of supports. The simplest one is just a cable or a rope, a chain, something like that. We have pins, we have rollers, and we have what's called a cantilever connection. These are the 4 we're going to look at. Now, a cable and a rope has a specific unique characteristic in which it can apply tension. So for example, if I have a rope and I tie it to something, I can pull on that rope and I can pull the object by putting the rope in tension, but I can't push on the rope. All right. So for example, here you see a weight hanging by a rope, but we can never have a flat surface and then have a rope going up and have a weight on it sitting on top of the rope. Ropes just don't work that way. They're too flexible. So this is our first one. And what we want to know is whenever I have a rope or a chain, it's only going to apply a tension force, and it's going to always be in the exact direction of the rope. So for example here, if I make a free body diagram of the weight, it has, of course, its own weight pulling down. And since this is a rope, I know that the force pulling up is a tension force, and it's pulling in the same direction that cable is. All right, here's a sign. So you would have a awning perhaps and a wall, and we have 2 ropes or 2 cables holding the sign. Now, if I made a free body diagram for the sign itself has weight, and in the same direction as both the cables, I have 2 tension forces pulling that way, and that would be my free body diagram. The tension of cable A, the tension of cable B, and the weight of the object. And of course, since this one's at an angle, we would want to make a note of what angle that is. All right. The second type of support is what's called a pin. Now, these are very, very common. We're going to deal with these a lot. A pin, imagine it's like an object that is hinged here. So think about like a door. And so the door sits on its hinges. Okay, this would be the hinge. Now, if I take this door and say we're looking at it from the top, and I push to the right, the hinge keeps the door from sliding off the door frame and moving to the right. If I would push against the door, the hinge is also going to stop the door from separating from the wall and moving into the room. Now, to counteract those two types of forces, the pin itself can apply forces both horizontally and vertically. Now, you might think, well, what about in a diagonal? Instead of saying, oh, yeah, it can stop things from going in a diagonal and putting a whole bunch of diagonal forces in here, we just say each diagonal force is just a combination of a vertical and horizontal force. So whenever we have a pin attaching something, we're going to replace that with a horizontal force and a vertical force. So 2 reaction forces, and that's what these are called, is reaction forces. All right, and the way we write this, instead of writing F, we're going to start writing R to indicate its a reaction force. Then the next letter right here, so we're going to say this is a reaction force at point A. So if this end of the bar is called point A, we'll say it's a reaction force at A, and this one's horizontal, which is the x-axis. So we'll say this is a reaction force at point A in the x-axis. This one is also a reaction force at point A, but it is in the y-axis because it's running up and down. All right. Now a roller, imagine this like a pair of roller skates. All right. If you're standing on a pair of roller skates, the wheel of the roller skates will stop you from moving down. Like it stops you from falling into the ground. It can apply a force up into your foot to hold you on the surface. But if someone pushes you side to side, it's not going to apply a force to counteract that. So a roller only applies one reaction force, and that's always perpendicular to the surface it's sitting on. So for example, if you're on roller skates, the surface you're on is the flat ground, it's horizontal, and your skates apply a force perpendicular to that, which means the force that they apply is a vertical force, and that's what holds you up so you don't fall through the floor. We don't want to say that this is always a vertical force because you can also put rollers on walls. So if I had a wall with a roller connection, that roller connection would push out horizontally perpendicular to that wall. So we want to say it's perpendicular to the surface it's sitting on. We do not want to say that it's up. All right. But the big thing is a roller is going to create one reaction force. And you see that here. We have a roller on point A. So this is still a reaction force. So it's reaction force at point A. And since this one is pointing in a vertical direction, that's in the Y. Since it only creates one force, there is no RAX, just RAY. All right. So if we were going to create a free body diagram for this beam here, notice I've got a force applied to it right in the middle. It's a downward force, and we have a pin over here, which we expect to create 2 reaction forces, one in the X and one in the Y, and a roller. And the surface the roller is sitting on, this little symbol down here represents the surface, this little diagonal lines. Since it's sitting on a horizontal surface, it's going to create a force perpendicular to that, which means it will create a vertical force. So when we draw the free body diagram for this, we're going to put on the applied force in the center, and we'll replace the pin with 2 reaction forces, one in the X direction and one in the Y, and we'll replace the roller with just one reaction force in the Y this time because it's sitting on a horizontal surface. The last type of connection, and this is actually the only time we're going to look at this one in this class, is what's called a cantilever connection. This would be similar to a diving board where it's only held at one end. Since it's only held at the one end, imagine you're standing on a diving board. If I push down on the diving board, this keeps it from moving down into the pool. If I push horizontal on it, this keeps it anchored. And if I apply force and it wants to twist out here, it creates a moment. So this has to create the moment that counteracts it. So A cantilever connection creates both an X, a Y force, and a moment. It has 3 reactions here, 2 forces and 1 reaction moment. All right, I want to bring that out. I want you to see it. We're not really going to use this much in the future, but perhaps someday we'll be doing something and it will come up. All right, so wherever you have a contact, we're going to have just a normal force pushing back against the object that's in contact with it. Cables and ropes will replace with tension forces. Pins replace with both a vertical and horizontal force, so 2 reactions. And rollers we're going to replace with just 1 reaction force. And if you do have a cantilevered thing, you'll have, just like a pin, a horizontal and vertical force, but you also will have a moment. We're not actually going to have any of those, but for your knowledge. Okay, so if I had something bigger, like this whole bridge here, notice a pin here, a roller here, I have another force here, maybe there's a car sitting on this bridge or something, and when I made a free body diagram for it, my pin gets replaced with these 2 reaction forces, my roller gets replaced with 1 reaction force perpendicular to the surface it was on, and the applied force stays where it was. All right, very good. So today in your homework, you're going to draw some free body diagrams for some objects.